Hello everyone, today I'll be teaching you simple harmonic motions, and before that let's start with periodic motion. So a periodic motion is basically a motion which which repeats after a certain interval of time. Example would be earth revolving around the sun or a pendulum swinging. So simple harmonic motion is defined as the motion in which the particles go to and fro in a straight line about a mean position such that the acceleration produced is directly proportional to the displacement. Here a is equal to negative ky because the acceleration occurs in the opposite direction to that of the displacement. So let's start with the general expressions for simple harmonic displacement and simple harmonic velocity and simple harmonic acceleration. So let's assume a body going in a circular path. Well, here the body obviously possesses circular motion and hence follows circular characteristics. But the foot of perpendicular itself is in simple harmonic motion, because if the body goes like this and if we have an axis around the middle right here, well, the foot of the perpendicular goes this up to here, then down, then up, down, which is simple harmonic motion. So let's say at a point P right here, this let's say is distance r, this is angle theta. Well, let's say this is r, let's say this is m from the x axis, let's say this is y axis, and this here is n. So here we can say that sine theta, well, it is equal to, well, this let's say is the displacement, right? So this is equals to y by r. So y is equals to r sine theta. And here, in terms of circular motion, we can write theta is equals to omega by t, which is angular velocity by time. So sorry, angular velocity is equals to angular displacement by time, giving us angular displacement equals to omega t. So here y equals to r sine omega t. Now this is the first equation, and this is called the displacement equation. Now here for velocity, velocity is defined as the rate of change of displacement with respect to time. So here this gives us r, and into the derivative of this, which is, well, using the chain rule, the omega comes out and becomes cos omega t. Now here we can write cos omega t using the trigonometric formula as r omega square root of 1 minus sine square omega t. Now what we can now do is we can put sine square omega t as y square by r square, right? The r goes down here, squaring both sides. This becomes 1 minus y square by r square, which we can take the r common, giving us r square minus y square by r square. So here this r will, the square roots cancel out the 2, so this and that in fact cancels, therefore giving us velocity is equals to omega root r square minus y square. That means that the velocity is maximum when y is equals to 0. So that gives us omega r, y equals to 0. That means when it is at mean position, namely over here. And v is minimum, that is v is equals to 0 when y is equals to r. So this is 0 when this is all the way up here. So here again, if you differentiate velocity, we get acceleration. Now here, if you have to differentiate this, that would be a bit of a work. So what about just, you know, derivative right here, which gives us r omega into, using the chain rule, minus omega sine omega t. So acceleration is equals to minus omega square r into sine omega t. Now here, r sine omega t is just y. Therefore acceleration is equals to minus omega square y. So here, this is a big equation that you'll have to use to derive that the other motions, such as a pendulum swinging and a spring mass system, is in fact a simple harmonic motion with this, in which you will need to require to find the time period and the frequency, and to show that A is directly proportional to Y. So let's start off with a pendulum. Now this is a very important topic. So let's say we have a rigid support like this, and initially the bob of the pendulum is here at position A. Let's say the length is rod, and after a certain time it travels around here, let's say A dash, through a displacement of y, and here, because of the displacement there, so let's say this angle is theta first, so here some tension is produced here, and the bob of the mass right down is mass into gravity, the weight, which gives us two vector components, namely the cos component and sine component. Here the cos component is this one, mg cos theta, which balances the tension, and here we have mg sine theta, which balances the force, right? Which balances the restoring force of the pendulum. So here mg sine theta, F is equals to minus mg sine theta, because they are acting on opposite directions. So mass into acceleration is equals to minus mg sine theta. Here we can cancel mass and mass. So acceleration equals to minus g sine theta. Now let's say that this angle is very small, such that sine theta will approach to just theta. So acceleration equals to minus g theta. Now what is theta? Well, here we know that theta is equals to the arc by the radius, which here is length, which is equals to the displacement by L. So we get A equals to minus g y by L, which we can rewrite as A equals to minus g by L y. So here gravity and the length of the rod remains constant, so we can write A is directly proportional to y. Therefore the swinging pendulum is in simple harmonic motion. Now to find the time period, we know from the acceleration equation that A equals to minus omega square y. If we compare equation 1 and 2, we can see that omega square is equals to, this would be minus omega square equals to g by L. So omega equals to root g by L, and we know omega is just 2 pi by time period root g by L. So which just gives us time period is equals to 2 pi root L by g. So this is the time period, and of course the frequency is just 1 by time period, so therefore the frequency is just 1 by 2 pi root g by L. Now here we get the time period, and we get to prove that this is in simple harmonic motion, so this is required for the pendulum part. I will cover the mass spring system and the angular simple harmonic